Hello and welcome back. In this video we'll finish up Chapter 8 with Section 8.4, which is on hypothesis tests, specifically on standard deviations and variances, although typically the standard deviation is what would be reported. So we'll focus more on standard deviations, but the process is still the same for variance. So the first very important thing to remember is that all of what I'm going to be talking about, the chi-squared tests, these require that the population that we're testing has to be normally distributed. So this absolutely requires it. This is unlike testing proportions and means. So for instance, with means, if it is normally distributed, great. If it's not, we could still use the techniques provided that our sample size is greater than 30. When we're looking at standard deviations or variances, we absolutely require that the population has to be normally distributed. Otherwise, this work doesn't apply. And because standard deviations are never negative, they describe how spread apart a data set is, so we can't have negative spread. The distribution is not going to be symmetric. It's going to stop right here at 0. The source of standard deviations we could get for a sample are always going to be positive. So it's going to be skewed to the right. And because it's not a normal distribution, it's called a different distribution. This is called the chi-squared distribution. We've seen a little bit of this before. This is how we calculate the chi-squared distribution, the chi-squared test statistic for our sample, where n is going to be the number of elements in our sample. S is going to be the sample standard deviation, the one that we calculate with our sample. Sigma is going to be the population standard deviation, the one that we're estimating. So this test statistic is what we use. We use it in exactly the same way as a normal distribution, or even the student t distribution. And one thing to remember is that this also requires the degree of freedom, just like the t distribution. So the steps, however, are exactly the same, and I'm going to focus on using StatCrunch for this. It'll make this a lot easier. So this is the example from the book in this chapter. So listed below are randomly selected female supermodels' heights in centimeters, and I list them here. And then the idea is supermodels tend to be a little bit taller than the average in the world, average sort of female height in the world. So what they want to do is they want to test whether or not the standard deviation of female supermodels' heights is less than the world average, which would be about 7.5, or maybe this is just the American average. But in either case, because they tend to be taller, maybe they tend to be closer in height to one another, which would mean a smaller standard deviation. So this is what we want to test. Using a 0.01 significance level, do female supermodels' heights vary less than, let's say American females' heights. So is the standard deviation less than 7.5? So we can begin by just writing down the claim is that the standard deviation of female supermodels' heights is less than 7.5 centimeters. So symbolically, what we're trying to say is that the standard deviation, so this is for the population of all female supermodels, the standard deviation of that population is less than 7.5. And when we write down our null and alternative hypotheses, the null hypothesis is going to be the same claim, except that we have equals in there. So this is the null hypothesis, and the alternative hypothesis is going to be that sigma is less than 7.5. Normally it's the same as, or we try to make it the same as some symbolic claim. So again, the null hypothesis will always have the equal sign. The alternative hypothesis will not have an equal sign and will either be less than, greater than, or just not equal to. In this case, we're testing whether or not it's less than 7.5, so we want it to be less than 7.5. Our significance level, alpha, is 0.01. This is just stated in the question. And for the test statistic and the p-value, rather than going through all of the calculations, we'll just use StatCrunch right here. So here I have all of the values, all of the 16 values that were listed in our question. So all of these heights, plug them into StatCrunch, and what we'll do is we'll come up to statistics, and what we're looking at is variance stats. Variance and standard deviations are essentially the same thing. Standard deviation is the square root of the variance. So what we'll look at is as variance stats. We have one sample. We do not have two samples. And the two options that we have are with data or with summary. These are going to be the two common options. Right now we have a data set. We have 16 values, individual values, and we're not summarizing anything. We have all of the data values explicitly. So we'll do this with the first data set. We need to select a column, so this is just the first column here, variable 1. And then this is asking us to perform a hypothesis test for sigma squared. But sigma squared is in fact the variance, and we want the standard deviation. But there isn't an option to change this. So we're just going to have to translate everything into variance. So if we come back here, the null hypothesis here is that the standard deviation is equal to 7.5. So what I'll do is I'll reword this in terms of sigma squared. So if sigma is 7.5, sigma squared is going to be 7.5 squared. And if you take 7.5 times 7.5, we get 56.25. Likewise, the null hypothesis becomes sigma squared is less than 7.5 squared. And 7.5 squared is 56.25. So when I plug this in, I want sigma squared is equal to 56.25, and the alternative hypothesis is that sigma squared is less than 56.25. And yeah, so there you have it. Again, StatCrunch does not allow for hypothesis testing the standard deviation explicitly. We have to use the variance. So you just have to square the standard deviation that we want. What I will also do is I will plot the p-values. This is completely optional. It makes no difference to the question, but it's nice to visualize it. There's no other things that I'll do. So I'll just click compute. And here we have it. So for our one sample, so this is going to be a variance hypothesis test, but we're going to use it to test standard deviation. They list the null hypothesis and the alternative hypothesis. The sample variance that they have here is going to be 3.4. So the sample standard deviation is going to be the square root of this number. Again, the variance is just the standard deviation squared. So to get the standard deviation from this, we just take the square root. We have 15 degrees of freedom because there were 16 values, and the degrees of freedom is one less than the number in our sample. Our chi-squared statistic, so this is our test statistic right here. So if we come back to Sideboard, our chi-squared statistic, is going to be 0.9066. 0.906, and then we can round it to 7, let's say. Our p-value, they also list right here, and it's a number that's so small, it's less than 0.0001. So they don't give the exact value there, but our p-value is less than 0.0001. So when we compare the significance level to our p-value, this is much, much less than alpha, our significance level. So because the p-value is less than alpha, we reject our null hypothesis. So coming back up, our null hypothesis was that the standard deviation was equal to 7.5, which we input into our system in terms of the variance, but our null hypothesis, our original null hypothesis, is that the standard deviation is equal to 7.5. So if it's not equal to 7.5 and we reject it, that means that the standard deviation is less than 7.5. So in conclusion, there is sufficient evidence to reject the claim about, to reject the null hypothesis, which means that our claim, which was that this standard deviation is less than 7.5, is true. To support the claim that the standard deviation of female supermodels' heights is less than 7.5 centimeters. So again, essentially we plug everything into StatCrunch and it tells us our p-values right away. So using that p-value, we can produce our conclusion.